Hello everyone, and welcome to today's Lab Tools webinar. I'm Nikki Spahich, Scientific Technical Editor for The Scientist, and I'll be moderating our discussion. Today, our speakers Tom Cottle and Dr. Peter Fung will be discussing generating thermal unfolding profiles on the Tycho system. We'd like our webinars to be interactive. We encourage you to send us your questions or comments at any point during the webinar, and the speakers will address these during the Q&A session following the presentation. To ask a question, simply click on the Ask a Question tab and type your query into the question box located on the bottom left of your screen. We'll try to address as many of these questions as we can during our Q&A session. Our webinar platform is user-friendly. You can expand the presentation window by simply clicking on the diametrically opposed arrows in the upper right-hand corner. This will maximize the display within your screen. The webinar will be archived on the Scientist website, and we will send you the link via email within a couple of days. Please note that you will not be able to download the presentation slides. I'd like to take this opportunity to thank our webinar sponsor, NanoTemper Technologies. The mission at NanoTemper Technologies is to enable everyone to do science that matters by always pushing the limits. NanoTemper is focused on making biophysical tools accessible to anyone looking to characterize proteins in any industry. Working with customers striving to make a difference in the world gets them excited. If you're looking to screen hits, measure binding affinity, characterize protein stability, or protein quality, let's talk. Our sponsors have provided us with some helpful resources related to the Tycho system, and we have posted these in our resource list located on the left side of your screen. You can access and download these documents at any time during the webinar. And with that, let me introduce our first speaker, Tom Cottle. Tom received a Bachelor's of Science in Biology and Biotechnology from Endicott College in 2015. He is a research assistant to in the Beth Israel Deaconess Medical Center's X-ray crystallography core. In addition to work at BIDMC, Tom has held previous positions and internships at T2 Biosystems, Cell Signaling Technology, and Alexion Pharmaceuticals. Tom?
Hi, everyone. Thank you so much for that great introduction. And I'm going to go over today a presentation that I call Accelerating Protein Purification by Using Thermal Unfolding as a Guiding Tool. And then just to very briefly, since it was already discussed, over my background and the background of our crystallography core. So as it was mentioned, I'm a research assistant at the BIDMC X-ray crystallography core. And what we do here is we provide services in protein expression and purification and crystallography. And we have lots of experience, as you can imagine, working with proteins, working with small molecules, and creating protein complexes. So the objective of my presentation today is to share with you our findings on methods to use the Tycho to improve our protein purification workflows. And more specifically, I'll be discussing rapidly identifying samples, optimizing buffers, denaturing and refolding proteins, the formation of protein complexes, the evaluation of small molecule interactions, as well as the evaluation of long-term protein stability. So I know we've been talking about, heard the name Tycho probably 5 or 6 times. You'll hear a lot more. So what is it and how does it work? So the Tycho can use up to 6 samples of 10 microliters, and you draw them into small capillaries and place them inside the device. Those samples are exposed to a thermal ramp from 35 degrees Celsius to 95 degrees Celsius, which slowly unfolds them. And while this ramp is happening, the Tycho detects the intrinsic fluorescence of the tyrosine and tryptophan groups within those samples at 330 and 350 nanometers. And the Tycho is very, very sensitive. It can detect really, really small amounts of sample, which I'll detail later in my presentation. But I would note at this time that this relationship is dependent upon the number of tyrosine and tryptophan groups in the protein. So samples that do not have many of these groups, they may not be detected well by the Tycho, though I personally have had success with as little as one tyrosine or tryptophan. And so here's an example of some data you might get out of a Tycho experiment. So the ratio of those two fluorescence values, the ratio of the 350 nanometer and 330 nanometer fluorescence, is plot on a graph against the temperature. And this gives us a nice curve, both in ratio and then the derivative of that ratio. And it gives us an inflection temperature, which is an approximate measurement of when the protein begins to unfold. So now, how can I apply the Tycho to my workflow, which is described here? As I mentioned earlier in the presentation, we're a crystallography lab, so you can see that we start with protein expression, then we move on to protein purification to kind of get rid of all of those other proteins that we don't want to crystallize, we don't care about, and then the final picture here, which shows a nice 1 microliter drop. It's got, I don't know if you can see on your screen, but it's got some nice little crystals in it that we then later were able to solve and provide structured data to our client. So how can I use the Tycho to make this process faster and better? As you can imagine, with protein purification, one thing we do a lot is nickel-based purifications with histidine tags. The Tycho allows us to rapidly screen samples that come off of nickel purification for the presence of protein to allow us to quickly eliminate fractions, or quickly eliminate samples. So in this screen, you'll see an orange trace and a pink trace. The orange trace came from our wash fraction, and the pink trace came from our elution fraction. As you can see on this slide, the pink trace has a nice, well-defined curve with a TI of just a little bit less than 50 degrees Celsius, whereas the orange curve is very jaggedy. There's lots of variance in signal, and though there is a slight curve to it, there's no clear transition. There's no the Tycho is not able to detect clear TI, and so from this data, we can roughly assume that our sample, or protein, is dominant in the elution fraction, and there's only trace amounts of relevant protein in the wash. And this sample took us, or this experiment, I'm sorry, took us about 5 minutes to complete, from loading the sample into the Tycho, running the experiment, and analyzing the data. That took me about 5 minutes. But as you can imagine, all of us in protein purification, we do lots of FGS page, so we're reliant on that technique. And so how does that compare to the Tycho? So I have a picture of my gel here that shows the protein purification, starting with the induced whole cell and ending with the elution fraction, with my protein of interest being slightly larger than 25 kilodaltons, as indicated by the arrow. This whole process of loading, preparing the buffers, loading the samples, getting the gel ready, running the gel, staining the gel, destaining the gel, and capturing this image took me about 1.5 hours. And I would say that this gel is still necessary because it gives me really good information about the purity of my sample and where in my purification I'm losing some of the sample. But the Tycho gives me quick assurance that my protein is, in fact, in the elution. And so while I'm running this gel, I can be confident that my protein is present, and I can move on to the next step of my purification, such as concentration or enzyme digestion, while I run this gel. So I can be more efficient with my time, and I can multitask if I have that solid result already from the Tycho. So on the next slide, I'll discuss, similarly, we do a lot of ion exchange-based purification. So I took this Tycho result from a cation exchange-based purification I did last week. You can see the dark blue line that's indicated with the arrow. That was my starting sample. And then the more purple line that's next to it, that is the sample that came out during one of the elution fractions. And you can see that not only is that trace quite similar to my starting material, it also is a little bit shifted forward in temperature, which might suggest that the increased salt concentration as the protein came off the column was beneficial to my protein's stability. And similarly to a nickel-based purification, I can see that the flow-through and the wash, my pink and my orange traces, quite similar to the nickel purification. They also have some curvature to them. They're also there, but similarly, the Tycho can't detect a TI, and we can safely, we can say that those probably aren't the proteins we're looking for based on their lack of similarity to the starting material and to the elution fraction. And I'll just show quickly, here is the chromatogram from that purification that I did. Those first two arrows, those are the flow-through and the wash, those pink and orange traces that I showed earlier. So we can see here that there is absorbance, there is protein there. And then the last arrow, that big spike in the purification, that is my protein of interest. That's that purple trace. So as you can see, you would want to analyze these three areas of absorbance. How do I know that this one, this very large peak coming off as the salt increases, how do I know that's my protein? Well, if I go back and I look at my Tycho traces, I can see that, as I was saying earlier, it's quite similar to my starting material. So, we can move on with confidence knowing that the increase in salt has improved the stability of our protein, and it's come off the column. And the last kind of column I'll discuss today is size exclusion chromatography. Similar principle to what we were discussing earlier, identifying areas of absorbance on the chromatogram and trying to rapidly identify those proteins using the Tycho. And we can see here that we've got three fractions from that largest absorbance peak, which have a nice, well-defined curve on the Tycho with a TI around 60 degrees. And then those other fractions on those other points of absorbance, they're flat or they exhibit very small transitions. Those aren't the proteins that we're looking for. But there are lots of other applications for the Tycho beyond just rapidly identifying samples off a column. One of them is protein buffer exchange and protein concentration. In this trace, I used a spin concentrator to increase the concentration of my protein down to a concentration that I can use for X-ray crystallography. And so the black line is the pool of fractions from before concentration, and the blue line is the concentrated protein. So we can see that the stability of the protein has slightly decreased, maybe 1 or 2 degrees, perhaps due to effects that are caused by the protein being more concentrated. Perhaps there's some aggregation happening. So that's something we should be concerned about. But what we can see that for the most part, those traces overlap and overlay, and we can be confident that our protein is still there and move on with our experiment. And as I mentioned, since we see that small decrease in stability, that's concerning to us. Why did the stability go down? Is there something we can change about the buffer to make our protein better? Can we make it more stable? So the next experiment we did was to dilute that protein into different tris buffers at different pHs. We took that concentrated protein and diluted it 10 times into those tris buffers as detailed in the bottom right corner of the slide. and then retested them on the Tycho. And I realized it's a little hard to see because of all the colored lines, but the blue line is our protein at pH 6.5, which is the least stable, and then the orange, pink, and purple lines are our proteins at 7, 7.5, and 8. And as we increase in pH, we can see that the protein becomes more stable. So now we know that when we concentrated our protein, some of the stability went down a little bit, but by using that step to exchange it into a higher pH buffer, we can get back the stability that we lost, which is really important to us. So now on to the information, we can move forward with our protein purification with this more optimized buffer. Some of the other applications of the Tycho are actually in the opposite direction. Sometimes we do protein purification where we're purifying proteins that are either insoluble or improperly folded. And so it can be beneficial to us to denature those proteins and purify them in their unfolded state. So in this experiment, I just resuspended a pellet in 6 molar guanidine hexachloride at pH 8, 1 millimolar DTT, and then I heated those proteins at 85 degrees Celsius for an hour. And I took a sample from that protein and I ran it on the Tycho. As you can see, there's no longer any evidence of a transition. There's no folding. The protein is just, the trace just goes straight down. There's no longer any folding there. And so we know that our denaturing step, our heat treatment step were successful. We know that the protein is now unfolded. And once we've unfolded our protein, the next step would be to refold it so that we can get it back into a usable state. And we use the Tycho for this as well. So once we've refolded our protein, we dialyze it out of that condition into the buffer condition described on the right of the screen. I won't read all those compounds off, but basically we incubated our protein at 4 degrees overnight, and then 3 rounds of dialysis into that new buffer. And after all that was done, we took a sample from that protein and we ran on the Tycho. And now once again we see that transition. The Tycho is able to detect the TI just around 60 degrees Celsius, and we can see that our protein has now once again become folded. And I think it's worth mentioning at this stage that after the various rounds of dialysis that we did, and the various denaturing and then concentrating and diluting into different buffers, at this point the concentration of our protein was approximately 0.07 milligrams per mil, which is quite low for us. And we're still able to detect it on the Tycho. So hopefully that speaks to those of you who are listening about the kinds of concentrations you might be working with and if they would be able to be detected by the Tycho. So for us, this is pretty low, but we're still able to see a sample at around 0.07 milligrams per mil. Another thing that we use the Tycho for is to detect the formation of protein complexes. So for one client, they asked us to have a complex between a 25 kilodalton protein and a 50 kilodalton antibody fragment. So we combined the two in solution, and then we separated away those samples by size exclusion chromatography. So you can see on this chromatogram we've got about 2 peaks of roughly equal height, roughly equal absorbance. One is bigger than the other, which suggests that it's the complex, and the smaller one would be the unbound protein. But how can we confirm that the complex is really formed? How can we confirm further that binding has occurred? The first thing we did was we ran a gel, both in non-reducing and reducing conditions. We ran 1 2 and 4 microliters of our protein complex. And we can see on these gels that both the antibody and the protein are present in solution. But what we can't really tell is just from a gel alone that any binding has occurred. We can see that they're both there, but we can't really see that the two molecules are interacting. But when we run these samples on the Tycho, we can see a pretty dramatic difference. The blue trace is our protein on its own, which has a TI of a little bit less than 60 degrees. The orange trace is the antibody on its own, which unfolds at around a little 74, 75 degrees Celsius. And the pink trace are those two samples combined into a complex. So there's two big key differences to observe here. The first is the increase in stability over both of the components. So while the orange line unfolds around 74 degrees, we see the pink line unfolding closer to 76 or 77 degrees. So there's a small increase in the stability of the sample. Also, we see an increase, we see a decrease, we see a change in the initial ratio of absorbance. You can see that the blue and the orange traces, they begin around a ratio of 0.7, but our complex, our pink trace, begins to unfold around at a ratio of 0.6. And this suggests to us that the ratios have changed because the total number of amino acids has changed. The total number of tyrosines and tryptophans that are giving off fluorescence has changed, which suggests to us that now they're bound together. There's a different amount of protein in that sample. And so these two factors together, both the change in the initial ratio and the change in the TI, suggests to us that our protein complex has formed. Another big thing we do here in our lab is work with small molecules. A lot of people come to us with proteins and small molecules that they want bound together, and then they want the crystal structure of that interaction so that they can be more informed about what their small molecule is doing to their protein of interest. And so in this experiment, I added that small molecule to the protein at a molar ratio of 1:1, and then I tested those samples before and after the addition of that small molecule on the Tycho to look for changes in stability. As you can see here in this first derivative graph, the black line is before the addition of that small molecule, and the blue line is after the addition of the small molecule. And so we can see a clear increase and shift forward in the TI thanks to the binding of that small molecule. And I can give some more examples. Because what if you don't want to do a ratio of 1:1? What if you want to do a smaller ratio, or more likely a bigger ratio? So in this experiment, I titrated in the small molecule in increments of 0.25 to 1 molar ratios. So first starting with 0.25, 0.5, 0.75, 1, so on and so forth. And you can see that this large peak down at the bottom, that's our protein in the beginning, no 0, that's no small molecule. And then as I slowly increase the concentration of the small molecule, we can see a gradual shift forward in the TI. And we see this change in the derivative where it becomes, the peak becomes less intense, and the center of that peak shifts slowly towards a more stable temperature as more and more small molecules added. And for us, we're able to see that more small molecules beneficial. But I would mention that we have used this experimental design in the past to evaluate how much small molecule is too much. We sometimes see that adding too much small molecule to a client's protein can have a detrimental effect on the stability, and we can actually see oftentimes on the Tycho, once we've added too much, then it becomes bad, and we know when to stop. So it really helps us to identify optimal amounts of small molecule to add to our clients' proteins. Once we make those proteins, sometimes we're asked to send them to our clients for either activity assays or for them, just to have for whatever other experiments that, I don't know what kind of experiments they want to do. I just, make the protein form and send it along. And before we send it, we like to freeze our proteins in liquid nitrogen so that they can be preserved while they're shipped. But something that is worth being nervous about is how does that freeze-thaw experiment, how does the freezing and thawing of the protein affect it? Does that damage it? Are there any problems with the protein becoming less stable as it goes through freeze-thaw cycling? So in this experiment, I took a sample and I snap froze it in liquid nitrogen, and then I thawed it out and took a small sample out and ran it on a Tycho. And I repeated that process 3 times. As you can see in this experiment, the dark black line, that is our sample before, and then the orange, pink, and purple lines are the first, second, and third freeze-thaw cycles. And there's very, very little change, no change even, on the stability of the protein. The 2 separate unfolding events that this particular sample had, they all happened at the same exact points after all 3 freeze-thaw cycles. And the traces, while not identical, are quite closely laid on top of each other. So we can, we have some confidence that our protein is relatively undamaged by freeze-thaw cycling. Another thing that's important to us is ensuring that each batch of protein that we make for a client or for ourselves for our own research is pretty close. They're pretty identical. The quality is equal between those batches. And the Tycho is quite useful to us in that regard as well. In this experiment, I ran samples from protein batch number T6 and protein batch number T7 on the Tycho, batch T6 being the black line and T7 being the blue line. And the TI of those 2 samples are perfectly aligned. They unfolded right back at the same temperature. There's some differences in the ratios, the initial ratios, most likely due to the difference in the concentration between those 2 samples. But we have assurances that the quality of our samples are very similar because they unfold, they have very similar TIs. So in summary, the biggest improvements to the protein purification workflow that we have here, thanks to the Tycho, has been a real increase in the confidence that we have of our protein's quality, as well as the rapid identification of our protein. Once we have a good feeling of, how does the sample react each time to the Tycho, how what temperature does it unfold each time. As we make many batches of our protein, we're able to really quickly identify the protein, and that saves us time to be able to move on to the next steps in our protein protocol while we run gels or while we run traditional methods to evaluate the successfulness of our purifications. And it's been invaluable for the optimizing of some conditions such as buffers, protein refolding, long-term storage and freeze-thaw cycling, as I mentioned, and of course, analyzing the conformation of the protein complexes or the activity of those small molecules, as I said. So I hope that was useful for everyone, and thank you very much for listening.
Thank you, Tom. Our next speaker is Dr. Peter Fung. Peter has over 23 years of industry experience developing, commercializing, and marketing products in the life science sector. Peter is currently the Senior Manager of Product Marketing at NanoTemper Technologies. He previously worked for BioCompare, Protein Simple, Molecular Devices, DiscoverX, and Scios Inc. He did a postdoc at UMass Medical, received his PhD in Molecular and Cellular Biology from Syracuse University, and a BS in Molecular Biology from Iowa State University. Peter?
Thank you, Nikki, for the kind introduction. Also, thanks to our audience for joining our presentation. I'd like to briefly talk about why it's important to study protein quality and how Tycho can be your everyday solution for a quick check on the quality of your proteins. So let me first share a scenario which hopefully will resonate with many of you who are doing protein purification. If you think about it, you spent the entire day or maybe even possibly the entire week optimizing and purifying your protein of interest. You've reached a stopping point in your experience and you need to store your proteins away. So you go to the -20 or the -80 freezer. You open the door and what do you see? It's basically a frozen tundra. Oftentimes there's no space left in the freezer, and frankly you think to yourself, can I really trust my freezer to store my precious samples? In a much larger question, I challenge you all to think about, do you really know the quality of your samples that you're working with? Whether you've isolated those samples yourself, someone has purified the material and handed it to you, or you take your hard-earned money and you purchase commercially of the protein that you want to work with. The question really becomes, do you know the quality of the material in those tubes, as oftentimes looks can be deceiving. If you think about some of the everyday tools that researchers have available to them to characterize proteins, I'm showing 3 common examples that are widely used by all researchers. The first on the left is UV spec or absorbance. It's great for looking at the concentration or purity of your sample. There's SDS page. If I asked anyone in the audience, have you run an SDS page, you'd probably say you've run thousands of gels. It's powerful technology for looking at the size or molecular weight of your protein of interest. And the last on the right is chromatography, which again is a powerful technology that's great for separating and resolving your protein from a more complex matrix of other materials. Collectively, these technologies have been around for almost 80 years, and while they're proven and widely used by all researchers, I'd ask you, wouldn't you like to see more information about your proteins? And that's why I'd like to introduce to you Tycho, the everyday solution for quick checks on the quality of your protein samples. So with Tycho, you can get multiple results on protein quality in a single experiment. So I should mention that here at NanoTemper, we think of protein quality as, we define it basically as the structural integrity or foldedness of your protein. So with Tycho, you can actually look at the presence, purity, similarity, functionality, and concentration of your protein sample all within a single experiment. You can get quick results on the protein quality, on your protein's quality, and do this in a label-free way, and it's only using a tiny amount of material. So how does Tycho do this? It utilizes a unique 30 degrees C per minute thermal ramp, so you can get your results in just 3 minutes time. As I mentioned, it's a label-free detection technology, so we're measuring the intrinsic fluorescence of your proteins, and this is from the tryptophan or tyrosine residues that are present in most proteins. Tycho uses only a tiny amount of material, specifically 10 microliters per data point to get your results. So you can use Tycho to check your protein quality and really improve all your workflow steps along that purification and characterization workflows. This includes the initial purification, the various chromatography steps you may perform, when you're working and characterizing the purified protein, or if you're optimizing those storage conditions of your material. And then finally, when you get to the assay development where you want to characterize your protein or test its functional activity. So let me just share with you, this is a quote from one of our Tycho users, Stefan Gajewski at Nurex, where he told us with his Tycho, I put every protein in Tycho first. The data is very reproducible in our hands. It's the only equipment I would recommend to anyone working on proteins because there are no downsides in having a Tycho. We launched Tycho roughly a year and a half ago, and to date we have almost 200 users that are globally located. And this includes academic universities as well as larger pharma and biotech companies. In this past year, we've had almost 9 publications, Tycho publications that have come out. And last year we were awarded as one of the top 10 innovations by the scientists. For us, this is really affirmation that the scientific community recognizes the importance of knowing protein quality. So let's talk a little more specifically about what you see in a Tycho experiment. As I mentioned, Tycho looks at the structural integrity or foldedness of your protein. The most important thing to remember is you're looking at folded protein becoming unfolded as a thermal temperature ramp is applied to your sample. So Tycho generates the following data. You'll get the initial ratio, which is the value of the ratio reading at the beginning of the measurement, and it serves as an indicator of the relative percentage of folded protein in your sample. The delta ratio is the difference between the ratio reading at the beginning and at the end of the thermal profile. Now, as I mentioned, since we're using this unique thermal ramp of 30 degrees per minute, we don't measure a true TM by definition. So we actually call this the inflection temperature, or TI. And this is essentially the midpoint of the unfolding event from folded to unfolded as you're providing that thermal ramp. Sample brightness can also be determined, and this is the sum of the fluorescence measured at 330 and 350 nanometers taken at 35 degrees. This reading can also be used as a relative indicator of sample concentration. And lastly, Tycho will determine the profile similarity for you using the software that's in the system. It's basically an index which quantifies the similarity between the unfolding profiles of 2 separate samples when compared to a reference sample. So what can you do with Tycho? As I mentioned, you can use Tycho to easily confirm sample similarity, do batch-to-batch comparisons, test various storage conditions and their effect on the unfolding of your protein. As you can see here in this example here, at -80 looks pretty good, and the unfolding profile looks similar to the reference sample, which was taken before the samples were put in storage. However, at 1 week at 4 degrees, you can see the unfolding profile is dramatically changed. You probably don't want to work with this material. You can also use Tycho for your buffer screening and assay optimization. In this example, we're testing the pH of different buffers and their impact on the quality of your protein samples. As you can see, the standard buffer is your reference. pH 5, you see a slight left shift in the unfolding profile, and pH 4 has essentially unfolded your protein. You probably don't want to work with this material. You can use Tycho to determine sample purity. As I mentioned, use these unfolding profiles and the inflection temperatures that are measured to detect impurities in your sample when you compare those to your reference material. You can imagine doing this along each of the steps of your purification protocol, and therefore maybe stop the process or optimize to reduce the impurities that may be coming along in that process. You can also use Tycho to validate the functionality of your protein. What's shown here is a plus and minus ligand interaction. So essentially, we're doing a quick test on either binding or interaction between 2 molecules as measured by that thermal unfolding profile. And as I mentioned, with Tycho, we're label-free, so you're essentially doing a label-free thermal shift experiment. And therefore, you don't have to worry about adding a dye which could cause artifacts in your results. results. So imagine using Tycho along each step of your purification process to make sure and confirm that your protein is retaining its functionality all along the process. Also, you can use Tycho to get an indication of protein concentration. If you run samples of known concentration, you can get their brightness signal, compare these, use this basically as a standard curve to compare your unknown sample and get a quick indication of the relative amount of material that you've been purifying. So again, you can use this throughout your purification process to see if you're enriching or if you're losing any of your target protein material compared to a reference sample that's stored in the instrument, so you don't have to run this each time the reference curve to get the concentration of your material. To date, our Tycho users have tested a wide range of proteins. These are just some of the examples that our users have looked at on Tycho. This includes antibodies, multimeric complexes, point mutations, membrane proteins, enzymes, and virus-like particles. Essentially, any type of protein can be examined on Tycho. So let me walk you through a couple examples of how our users are employing Tycho in their protein purification and characterization workflows. In this first example from our Tycho users at the ETH in Zurich, they run a lot of SPR binding interaction experiments. What's shown in this example is a model protein, carbonic anhydrase, that's used as basically a control in SPR assays. It's known to bind to a series of different compounds, and what's selected out here are weak, medium, and strong binders. This particular group used to use a thermal shift assay prior to running SPR assays as a quick check, but since now they've incorporated Tycho to do the process, and what's shown here is that with Tycho you can still get a similar rank order of the different compounds binding to carbonic anhydrase, what they observed using the thermal shift assay, but more importantly, corresponding to the results that they expected to see with their SPR analysis. The important take-homes from this is that both the sample prep and the time to results is about 2 times faster using Tycho compared to a traditional thermal shift assay, and you use a lot less protein, about half the amount compared to what they needed to use when they were running their thermal shift assays. And as we mentioned earlier, there's no addition of dye, so you don't have to worry about any secondary effects or questionable results that may come by that dye addition to your sample. You're testing the native material. In the next example, what's shown here is just a quick test for characterizing a monoclonal antibody. As you know, monoclonal antibodies are an important biotherapeutic target, and it's important to understand the stability of those targets, and a quick test is to do an oxidation experiment to see the impact on the monoclonal antibody and its binding abilities. So what's done here is both a 3-hour and 18-hour hydrogen peroxide treatment. As shown on the left are the Tycho results. The gray trace represents the native control material, and as you can see, both the 3-hour and 18-hour in teal and purple respectively, there's a left shift in the unfolding profile of these two conditions. To confirm the effect of the hydrogen peroxide treatment destabilizing the monoclonal antibody, we took the same samples and ran them on our monolith system, which is our technology for looking at binding interactions. And you can see that the results on monolith confirmed what we saw on Tycho. The native condition gives you a binding affinity of 1.4 nanomolar, and there's a right shift upon hydrogen peroxide treatment, therefore allowing you to use Tycho prior to running more complex, more detailed experiments to get an idea of what are your best candidates, are you seeing functional activity, and allow you to sort of set the basis as you go in to do these more detailed experiments and work with the most important samples that'll get you your results. So we believe that Tycho is the everyday solution for quickly checking protein quality. You can identify the quality of any protein sample in just 3 minutes time using only 10 microliters of material. You can test the sample integrity, the similarity, functionality, purity, and concentration all in one experiment. And that Tycho can really integrate into any step along a purification workflow and really help you with the assay development and optimization as you're characterizing the function of your proteins, really helping you to make the entire processes more efficient. So at NanoTemper, we're focused on helping the researchers find solutions to help better characterize their proteins. We have an entire product line including Prometheus, which is the new gold standard for precise characterization of protein stability, Tycho, which I've talked about today, the everyday solution for protein quality checks. We have Monolith, which is our flagship product line, and it's the choice for measuring molecular interactions. And just this year, we launched Dianthus, the high-throughput screening solution for measuring binding affinities. And with that, I'll say thank you for your time,